Okay, we're still working with vectors, and we've been doing some math with vectors, and in the last video we looked at sort of adding and subtracting vectors. So now you may think, well, is it possible to like multiply vectors? And we sort of multiply vectors. We don't call it multiplication, and it has some unique purposes. Actually, instead of multiplication, they have what's called the dot product. The dot product is sort of like multiplying two vectors. Matter of fact, if I give you two vectors, vector v is 2i plus 6j, and then vector w is I minus 2j. To multiply them, we don't call it multiply, we call it take the dot product. It looks like a multiplication sign. So we say the dot product of vector v and vector w. Let me actually go over here and define it. Let's say in the general case, we'll say vector v we'll call a times vector I, unit vector I, plus b times unit vector j. Actually, we'll call them a1 and b1. Vector w would be a2 times I plus b2 times j. Then the dot product is actually very straightforward. You take the I parts of the two vectors and you multiply them together. A1 times A2, and then you add the product of the j parts of the vector. That's the dot product. Now what's interesting, when you're done with this, turns out when you take the dot product, in some strange way, it ends up being a number, it's not a vector. So when you take the dot product of two vectors, somehow the vector part goes away and you're just left with a number. So now knowing that, when I go over here to my actual v and w vector, v dot product w would be 2 times 1 plus 6 times negative 2, 2 minus 12, looks like the dot product is going to be negative 10. So not very difficult. Now there's really one very important equation which I'm going to give you, and in the book you can see how it's derived, but I'm not going to take the time to derive it. But this important equation actually involves a dot product. And because of this equation, this is going to be the reason why we're going to do some problems where we have to be able to do the dot product. So this equation involves two angles. We'll still use angles v and w. So if we have an angle v, or a vector v and a vector w, and just for fun, so they look like that, and there's the angle in between. There's this very interesting sort of formula that says the cosine of the angle in between the two vectors is equal to, in the numerator, you have the dot product of the two vectors divided by the magnitude of vector v times the magnitude of vector W. Very interesting little formula. Now we're going to really use this for two purposes. And let me tell you what we're going to do now, and then we're going to just do some examples. The first purpose of this equation is to find angle between two vectors. Right? If you have two vectors and you want to know the angle in between them, you take the dot product of the two vectors divided by the two magnitudes multiplied, and that equals a cosine of theta, which is the angle between the vectors. Then theoretically, if you take the inverse cosine of both sides, you would have the angle. So we'll do a couple of examples where this formula allows us to find the angle between the two vectors. Now, the second purpose, which is somewhat related, you're going to occasionally have problems where they're going to give you two vectors, and they're going to ask you to answer this question. Are those two vectors parallel to each other? Now, this word orthogonal means the same thing as perpendicular. The two angles, are they 90 degrees apart? But then the third option is neither. And one little added note that you'll see in a minute, when we say if we end up having two vectors that are parallel, we also have two kinds. Sometimes the vectors go in the same direction. Sometimes the vectors go in opposite directions. They're still parallel, but sometimes they head off in the same direction, sometimes they're opposite direction. So let's take these one at a time, and let's see how this formula allows us to do these two things. So first, let's just take two vectors and try and find the angle in between the two vectors. So for instance, say vector v is negative 4i plus 3j, and vector w is negative 6i plus a negative 2j. Once again, almost all these problems, a sketch can really help just to keep you from making mistakes. So let me sort of sketch these two vectors and see what the angle between them would look like. Negative 4, 3. So let's go negative 4, 3, negative 4, and the sort of negative x direction in 3. Maybe right here, so maybe this would be like vector v. And this w vector, negative 6i. Oh boy. So we got to go even further out. And negative 2j. So maybe the w vectors so the angle in between is the smallest angle. And that's what we're trying to determine. Well, if I use the formula that we were just talking about, cosine theta in this case would be, well, let me just write it out since this is still new. Dot product of VW over the magnitude of vector V times the magnitude of vector W. So let's see if we can fill this in. So the dot product, so you go to vector v, you get the I part, -1, times the I part of the w vector, plus now you get the j part of the v vector, 3, times the j part of the w vector, which is -2. Magnitudes, right? Magnitudes are where you take the square roots of the I and the j parts. So -4 squared would be 16. 3 squared is 9. -6 squared is 36. -2 squared is 4. So now, of course, this becomes square root of 25, which is just 5. And this is square root of 40. I could simplify this, but because I'm going to use my calculator, it doesn't really serve me any purpose. So 40 square root times 5 equals, and actually this is 24, this is -6, looks like it's, the numerator is 18. .57. So then the angle in between them is this inverse cosine, 55.3 degrees. And that looks reasonable. All right, so really that part of it, not too difficult. To find the angle between two vectors, just apply the equation and you're good to go. Now let's look at this second way we're going to use this equation. And that's where you're given two vectors. And they ask the question, are these two vectors parallel, orthogonal, which means perpendicular, or neither? And if you think about it, let's just think about it for just a second. Especially let's think about the perpendicular. So here's my equation with the two vectors. If you think about, let's think about two angles that are perpendicular. Let's just do the first one on the x-axis to keep it simple. So orthogonal or perpendicular means the second, so say we'll call this vector v, and we'll call this vector w, and that's like 90, oh, I'm not going to, oh yeah, 90 degrees. Let's look at what happens when we plug in a 90-degree angle into this equation. So really you have cosine of 90 degrees. Now what is the cosine of 90 degrees? If you think about the unit circle, the cosine is like the x value. What's the value of x at this point up here? Well, it's 0. So what you really have is 0 equals the dot product of VW divided by the magnitudes. Now if you think in a math sense, the left-hand side is 0, and I've got this stuff over here, even though I don't have any numbers over here, I can sort of make some conclusions. First of all, what's the only way that this fraction here is going to ever equal 0? The only way it's going to ever equal 0 is if that numerator equals 0. There's nothing I can do with the denominator to make this thing ever equal 0. It's just not possible. I can't do that with the denominator. However, if the numerator is 0, 0 over anything is 0, and then we know we have perpendicular vectors. So really, I'll call them orthogonal like the book does. 4 orthogonal vectors, which means 90-degree vectors, the dot product of the two vectors has to be 0. Now let's think some more. How about if the vectors are parallel vectors? So here's my v vector. Now parallel vectors, there's two possibilities. I could put the w in the same direction. Let's see what happens here to our equation. I know for those parallel vectors, what's the angle between those parallel vectors? Well, obviously it's 0. What's the cosine of 0 degrees? It's just 1. So basically, if I'm given two vectors, and I want to find out whether those vectors are parallel and head off in the same direction, you just do this math, and if this fraction here equals 1, then you've got two parallel vectors in the same direction. What would happen if, here's my v vector, there's my w vector. We say that those two vectors are parallel, but they head in opposite directions. So what would we say the angle between these two vectors is? (180 degrees, right? So what's going to happen to this equation? Cosine of 180 degrees. What is the cosine of 180 degrees? Well, it's -1. So now this equation becomes -1 equals the dot product of VW over the magnitudes V and W. So the key is, for this one, parallel, same direction. If it's -1, they're still parallel, but they're opposite directions. So big picture, here's what we're going to do. You're going to be given two vectors, and you're going to be asked, are these vectors orthogonal, parallel, or neither? And if they are parallel, do they go in the same or opposite directions? That's going to be the question. And it's actually a pretty simple procedure to answer the question. Matter of fact, let's just go ahead and do a couple of example problems. How about vector v oh, that's nice. Now we're dealing with fractions, which should be fun. There's vector v, and there's vector w. What we're going to do is, first step, you take the dot product. If the dot product's 0, then you know the two vectors are perpendicular or orthogonal and you're done. If the dot product is not 0, then you go ahead and I'll say calculate the formula or the whole equation. And if that whole formula equals either 1 or -1, then you know you have parallel vectors, either the same or opposite direction. And if it doesn't equal 1 or -1, then you know you have neither. So let's do this first. Let's see what the dot product is between V and W. So -3/2 times -6, I think is 9. Two times 8 is 16. Looks like the dot product is 25, so I can say they're definitely not orthogonal. It'd have to be 0 for them to be orthogonal. So now the question is, are they parallel? The only way I can determine that is to actually perform this calculation. I've already done the dot product, which is 25. Now I got to find the magnitudes of these vectors. So for V, -3/2 squared plus 2 squared, whole thing square root, -6 squared plus 8 squared. So 25 over, that's what, 9/4 plus 4? Wow. It's like 1625 over 4. Times 36 plus 64, is that 100? Five halves times 10. Lots of algebra here. I hope I don't mess up. Lo and behold, it looks like it's 25 over 25, which is 1. So you'd say those two vectors are, maybe I spelled this wrong, parallel. Same direction. Let's do one more. How about vector V? -6i plus 18j. Vector W. (9i plus 3j). And we're asked, are these two vectors orthogonal, parallel, or neither? First thing we do is check the dot product. -6 times 9 is -54, plus 18 times 3 is 54. Lo and behold, the dot product is 0, which means we'd say the vectors are orthogonal, or we could also say perpendicular. Now, I'm not going to do an example now, but if you were to happen to have two vectors, the dot product is not 0, and you went and did this little formula here, and it's just any other number but 1, then you would say you have a neither. The angle is not either 90 or the lines are not parallel.